Okay, so this is our fifth video in the final unit here. This is kind of a continuation of the previous one. The previous one was a concept of integration by a substitution, and the idea there is just to have a way to undo a chain rule. So today what we want to do is integration by parts, and this, as you can see right here, integration by parts is a good way to undo a product rule. And so what we're going to try to work on today, as you'll see in the examples, is some fairly challenging looking derivatives where there's like x times by cos 3x, or there's x squared times by sine 3x, or x squared times by ln x, where you can kind of see that there was a product rule perhaps applied here. And we have to try to find a way to undo that when we do our integration. And so first I want to show you the proof for how this worked. And you don't actually have to do this proof going forward. You just need to know how to use the rule. But here's how it was discovered. Imagine what you have here. I'll just try to highlight as we go along here. Where's my highlighter? I'll just use a yellow one here. Imagine as you go along right here that you've got a what should have been a product rule, right? And we know the product rule is the first times derivative second, second derivative first. But let's say that you want to take that stuff right there and you want to reverse it. Well, then isn't this stuff right here, when you integrate it, doesn't it take you back to there? Isn't that what this notation here means? If you antiderive this bit right here, it would give you the original. Well, what we could do, though, is we could apply an antiderivative sign to the first half of what would have been the product rule and the second half. So you can see how right here I've antiderived both of these pieces right here. And then for the last little bit here, what we've done is we've taken the f prime and the gx that was on what's currently my left-hand side, and it was brought over to the right-hand side, and it formed this formula. And this formula here is kind of tricky because in order to antiderive something, this is what you're going to antiderive. You're going to antiderive two things that are multiplied by each other. One of which is a normal piece of function. The other one which happens to be a derivative. And then what ends up happening is you can find what this thing is equal to by making it equal to two original pieces, but you actually have to take an extra antiderivative to solve your first antiderivative. And if your head is spinning, that's okay. Like, I just need to show you some examples here. But the basic concept is we can find an antiderivative. This is us finding an integral. And in order to find it, it may actually require you to take a second antiderivative to do so. So this formula gets written in a couple of different ways. This is one that I like. It's f of x g prime is equal to f and g minus f prime and g when you antiderive them. So it may just be best just to hop right into an example. And so why don't we try that here? What we need to do is we need to make one of our pieces be an original function and one be a derivative. So in this one right here, what we may discover that it's best to let f of x be equal to x and to let g prime x be equal to e to the x. And so it's kind of like substitution here. If that's what you have going on right there, then what you can do here is replace this bit here with f of x. So this right here is x. And then you're going to need g of x. Well, I don't actually have straight up what g of x is. I have g prime. But hang on, if g prime is e to the x, that's really what I'm asking you to do is antiderive. Right? So if the derivative is e to the x, well, wouldn't the original have also been e to the x? So from here to here, this is just regular, by the way, then really I'm actually asking you to antiderive this little bit as well. So if this was a prime and this one is a non-prime, I need to antiderive. But the good news here is that g of x is just the same thing as g prime because it was e to the x. Now I still need to antiderive f prime. Well, I actually don't know what f prime is. I know that f is x, but I could figure that out by finding f prime, and that would be 1 then. So I'll make that equal to 1. And then I need what g of x is again, which, okay, it's a good thing that I found that, right? Because g of x, I just wrote out a second ago, is e to the x. So the tricky thing about this is that you're actually taking multiple antiderivatives. G prime I defined right here as this guy, but I actually have to find what regular g is in two different locations. So I have to find the antiderivative. I have to antiderive here, and I have to antiderive right here. And then there's still an extra antiderivative sign right here, so I still have more to do. I also had to take a derivative. I had to take a regular derivative to be able to turn f into an eventual f prime right here. So what I'm now being asked to do is do x e to the x minus, and then I have to antiderive an extra e to the x. But doesn't e to the x just derive to e to the x? So there. This is now my derivative, or sorry, my antiderivative. I'll write it as f of x, capital F of x. Now, I mean, you might be blown away and go, oh, wow, hang on, can that really be true? But let's test it using derivatives. Let's just rederive. So this first little bit would be a product rule. It would be the first times the derivative of the second plus the second times the derivative of the first. And then I'd have to also derive this e to the x, but it derives to itself. And watch, this e to the x right here will actually cancel that minus e to the x right there. And you'll be left with x e to the x, just like we started with. So I've shown you one, and usually the way I find derivatives, antiderivative, integrating, there's the word I'm looking for, integrating by parts, the best way to do this sometimes is just to show you a bunch of examples. So at the end of the day, here's how this formula works though. You have to take the two pieces that you're given, and you have to identify one of them in which you're going to derive. You have to also identify another one in which you are going to antiderive. You're then going to take the derived piece of this one, the antiderived piece of this one, multiply them together, and then antiderive it a second time. And if this works, this is a clever way for you to find an antiderivative. So now sometimes I like this formula better. Rather than writing it using f of x and g of x, which means you need to use primes, I like writing this notation. So this is my preferred one. This is u dv equals uv minus antiderivative v du. So basically you need to have something that is a normal function, and you need to have something that you're going to define as being a derivative. Now the normal function gets rewritten right here, but to go from here to here, you're going to have to antiderive. So this thing right here better be something easy to antiderive. It's also going to go right here as well, by the way. Now this piece of function right here, whichever one you designate right here, it has to be something that can be derived and be differentiated. Because then when you're done, you'll have to take these two pieces together, multiply them, and then antiderive a second time. So doing this by parts involves some deriving, some antideriving, and then some extra antideriving. So this is quite long. So let's do some more examples here. What we need to do is identify the two pieces of this function. And hopefully it's clear that the two pieces are definitely x and cos 3x. So what we have to do is figure out one of these pieces which we're going to derive and one which we're going to antiderive. And I usually like to write them as, let's see, what are the letters we use? We're going to use u as one of them, and dv as the other. So I got to pick which one's going to be u and which one's going to be dv. Now, usually the general idea is that you want to pick the thing that's easy to derive, and hopefully it even turns into a constant term. That's what you want to be the u. So I'm actually going to make x be my u. And the reason why is that when I want to then find du, that's going to be 1. And that makes a lot of sense to make my x be the u value, because then when I need the derived part of it, that's a 1. Well, that means that by default, my dv has to be cosine of 3x, which means I'm going to need to figure out what v was. I need to antiderive this dv back to v. So I got to figure out, well, what would it have been? So hopefully you can just use your own kind of common integration concepts and figure out that it would have been sine 3x over 3. Because what ends up happening is if you were to have derived the sine, it would give you the cosine. The 3x would have stayed in brackets. It would have needed to times by a 3, but since there's not a times by 3 here, we need to divide by 3 instead. Well, now I have my pieces, hence the term integration by parts. There are now 4 pieces that I have here, a u, a du, a dv, and a v. And so now I can apply my formula. So if I want to antiderive u by dv, which is x by cos 3x, what is that equal to? Well, it's equal to u times v minus the antiderivative of v times du. So let's start plugging in pieces. U I've defined as x, and v I've defined as sine of 3x, and this will all be over 3. So that part's the easy part. I've antiderived the dv to get me v, and I now know these two terms. But the next piece right here requires me to still do an extra integration. So then v is sine of 3x over 3, and it's going to need to get multiplied by whatever du is. But here's the linchpin to the whole thing. Since I picked x to be u, and it derives to du, which is 1, when I times by 1, really I don't actually have to times this by anything, because timesing by 1 doesn't do anything. So my antiderivative is equal to x sine 3x over 3, but I still have an extra antiderivative to take. So then I have to figure out, well, how do I get a sine? And sine would have come from a negative cosine of 3x, but it would have had to have been divided by an extra 3. Right? Sine comes from a negative cosine, because cosine derives to negative sine. So if you want this positive sign, you want a negative cosine. You have to divide by another 3. So long story short, our final answer is x sine 3x over 3 plus cosine of 3x over 9 plus c. There is our antiderivative. Now this is challenging to check, but we should be able to. So I'll stop right here. I'll put a big star next to what my answer is. Now let me try checking by deriving it. This would be the first times the derivative of the second plus the second times the derivative of the first. So that's really what I did right here. And then this guy right here isn't a product rule. It's just straight up just derive it. So cosine derives to negative sine, chain on the 3, and then when you derive the plus c, it gives you a 0. So these 3's will cancel. That'll leave you with x cosine of 3x. And then here's how this was designed to work. Look, this guy right here is sine of 3x over 3. And this guy right here, although it's not written that way yet, if I do some canceling and make that 1/3, this is also sine of 3x over 3. So really this term and this term are the same as each other. One's positive, one's negative, they cancel. And so yeah, now I have my original. This is what my original function would have been. And then going from here backwards, that's my antiderivative. So this takes some practice. It takes a lot of getting used to. This is really a lot of the meat of a good calculus course, is being able to solve integration by substitution and integration by parts, because these are powerful tools for being able to solve some really challenging antiderivatives. So you're going to want to put some practice into these. You don't just want to watch me do them once or twice. If you can, find a textbook and find the chapter that's going to have integration by parts and by substitution, and get some good practice on these, so that when you get to university next year, you'll have seen some of these before. So, okay, so let's try this one here. Now, this one's even more of a challenge in terms of trying to solve, because again, I've got to try to figure out who u and v are going to be. And sometimes this takes a little bit of trial and error, which sometimes students are not willing to have like the first and second takes at things. Similar to maybe the word problem unit we just finished, you have to be willing to spend some time trying and going, that didn't work. Okay, let's try something else. Oh, that didn't work either. Well, like on this one here, you really have two choices. Either u is going to be the x squared and dv is going to be the sine of 3x. Or it's the other way around. Well, or it's this way here. And sometimes you just have to try both of them and figure out, well, which one is going to be the one that can help me solve. And you may end up discovering, actually, that by parts is not even possible. And you have to try a different sort of trick, because there's more different methods of integration than just parts and substitution. But those are the only two we're going to cover for right now. But there are more different ways of doing this. So I'm going to try going with this orientation. I'm going to try going with x squared for u and dv for sine of 3x. So, but I had to pause that example there. So the two of you who called me, you know who you are. This was that moment. Anyways, it's okay. I'll re-pick up the lesson. I believe what I was doing before I paused was to try to figure out what u and dv were going to be. And I think I was trying to like flip them around and say, well, this one could be u and this one could be dv, or you could do this one there and this one there. Sometimes it just takes trial and error. It just takes the willingness to just go out on a limb and give an attempt at it. sometimes you can kind of see a few moves ahead. And I have a little bit of an experience, so I'm going to try this one here, and we're going to see where it goes. So this one I'm going to make be u. This one I'm going to make be dv, which means that my formula for that is equal to, pardon me, u times v minus the antiderivative of v times du. Okay, so u I have. U is x squared. V I do not have, so I'm going to have to try to figure out what the antiderivative is. So going from the derivative backwards is going to be a negative cosine of 3x over 3. Hopefully that makes sense to you. Cosine would derive to negative sign, so negative cosine derives to positive sign, but you have to divide by 3 to account for that chain rule. So I'm gonna throw the negative here. I'll make it negative cosine of 3x over 3. And then I'm going to have to use that again, so that's another negative cosine of 3x over 3. And now I need what du is. And du I haven't actually written out yet, but it would be 2x. Okay, well, I mean, I can do a couple of things here. For example, I can make this now be negative x squared cos 3x over 3. And there's a negative sign here and a negative sign here. Why don't I just make it a positive sign here? And I'm going to change the order that I write things in here too, just because I don't love the order they're written in. I'm going to write it as 2/3 of x times by cosine of 3x. There. Now here's the downside. I still have to antiderive this little bit right here, which means that I might actually have to use a second set of integration by parts, because again, I really have a part right here and a part right here. This is kind of like a chain rule within a chain rule within a chain rule, only this is like by parts within by parts. This guy right here is done, and he will be done for forever. That minus x squared cosine 3x over 3 is always going to be there. But this little bit right here, I'm not ready to integrate it yet, because I don't know how to integrate the, I shouldn't go too far there. I don't know how to integrate the 2/3 x times cos 3x. So I'm going to have to remake this into like u and remake this into v. And you'll discover that with experience, this helps a little bit, because you're always looking for your u to be something that when it derives to a constant term. And then that means that my dv from this little bit right here, well, when I antiderive it, it becomes kind of ugly, which is fine. I can live with that. So that would have been sine of 3x over 3. But now I reuse my formula here again. So this is going to be left here the entire time. Okay, so the formula is u times v. So u is that, and v is this. Then I have to subtract the antiderivative of v times du. So hopefully you can figure out where that came from. This is u right here, 2/3 x. This is v right here. This is like my second iteration of u and v, by the way, right? Up here was my first u's and v's. This is my second set of u's and v's. And then here's my v again a second time, and there's my du. Now the key to this is that you want your du to preferably be something that derives to not have a variable in it. Because as a constant term, here's what I'm left with when I clean it up a bit. I've got negative x squared cosine of 3x over 3. I've got 2x sine of 3x all over 9. And then this guy right here, before I antiderive it, is really 2/9 sine of 3x. Well, ignoring the 2/9, I can antiderive sine of 3x. Sine would have come from, okay, again, sine comes from a negative cosine of 3x over 3, but then there's still that 2/9 in front. So, final answer. We're almost done here. It's negative x squared cos 3x. That was carried down the whole way. This next term kind of gets carried down the whole way as well. And then on this last one right here, it's a negative negative, which means it would be positive 2 cosine 3x over 27. One of the things you might notice, by the way, is that with some of the way these chain rules work, this one had an over 3, this one's over 9, this one's over 27, because each time that I undid the chain rule, I had to add an extra 3 on the bottom to account for when you derive it, you get an extra 3 there. And don't forget plus c. I know it seems like it's a silly little thing, but if this is an indefinite integral, we have to put plus c there. So there's my antiderivative. So quick thought here. We should be able to reasonably quickly re-derive this and get an answer. So I'm going to do the first times the derivative of the second. So cosine derives to negative sine plus the second times the derivative of the first. So that's what this bit right here gives me. Then this next one here has got a similar issue, so it'll be the first times the derivative of the second plus the second times the derivative of the first. So that's this guy right here. And this last one doesn't even require a chain rule. It's just, see, cosine derives to negative sine. There, so now I have 5 terms. Now watch carefully as how these 5 terms work here. This 3 and 27 really becomes 1/9. But with a 2 there, it becomes 2/9. Here you have sine of 3x, here you have sine of 3x. This gives you 2/9, this gives you negative 2/9. This term and this term, they would have canceled. Right here, this 3 and this 9 would have canceled to give you a 3. Well, here you have a cosine of 3x. Here you have a 3. Here you have a negative 2x. Here you have a positive 2x. These two things would cancel. This 3 would cancel with this 3. This negative sign with that negative sign. What you'd be left with is an x squared and a sine of 3x. And I know it's been a while since we started this question, but yeah, we want a x squared and a sine of 3x being multiplied by each other. So this guy right here is the antiderivative. This required an integration by parts inside of a second integration by parts. So that is something that could come up. Okay. Let me try one more here. On this one here, again, we're trying to break it up so that we need a u and we need a dv. And again, one of these is going to be x squared, one's going to be ln x. And sometimes you just have to try and see, well, which order makes sense. And so I think the way this one works is I'm going to try doing this one first just to give it an attempt here. This is going to be u times v. So now I need to know what v is. What's the antiderivative of ln x? And it's not 1 over x, by the way. That's what the derivative of ln x is. Oh, I don't actually know what the antiderivative of ln x is. So sometimes you may just start on a path, like I just did there on purpose and didn't get anywhere, and discover that actually, maybe I should go the other way around here. Maybe I should make my u be ln x instead. So again, this is equal to u times v. Okay, well, I don't have v. So v would be the antiderivative of x squared, which would be x to the 3 over 3. So there's what I'm looking for there. Then we need to take the antiderivative of v. Okay, so that's my x to the 3 over 3 again. And then times my derivative of u. Well, my derivative of u, du, would be 1 over x, because the derivative of ln is 1 over x. So. Well, now normally we want this guy right here to be a constant term, but that doesn't have to be the case, because watch this. I have ln x times by x to the 3 over 3. Before I antiderive it, look, this and this one cancel, giving me 1/3 of x squared. Well, I can antiderive that. I'm going to clean this up a little bit. I'm going to throw the x to the 3 and the 3 in the front, just so that I don't somehow think that that's part of the natural logarithm. And then when I want to antiderive this, it becomes x to the 3 over 3 plus c. So my final answer is x to the 3 ln x over 3 minus x to the 3 over 9. There, plus c. Don't forget the plus c. Now that's a good place to leave it. You could, in theory, do this and make it 3x to the 3 ln x minus x to the 3 over 9 plus c. You could even factor and make it x to the 3 bracket 3 ln x minus 1 over 9 plus c. But really any of these should work, so I would be fine if you just had left it as this line right here. But you should always ask your professor kind of what their expectations are, because a common expectation could be that if you have if you have uncommon denominators, to make them common denominators. That's what I did in this step right here. Those wouldn't have been there anymore. And you also could be expected to factor things. You even could have bring this x right up there and bring it up as an exponent using your logarithm rules. But again, this doesn't really achieve much purpose. So. Okay, well, that's actually it for the topic. I've got 3 examples. This only took 25 minutes. It really would be a good idea to rewatch this again, because in these 3 examples, I would have shown you an example here where you're looking for the derivative to hopefully be equal to like a constant term. Or in this one right here, I wasn't actually able to make the derivative equal to a constant term, so I had to actually do it a second time and do an integration within an integration. Or it may be possible that you sometimes just have to kind of flipping around which one u and dv happen to be, because maybe you're not really sure whether that one should be u or whether this one should be u. I actually once had a university, one of my former students who went to university, end up showing me a question. I thought this one was really cool. He needed to derive, like, antiderive a times b. And when he did it by parts, he ended up getting the, you know, like, ab minus the antiderivative of you know, CD or something like that. But then when he ended up having to solve for that antiderivative a second time, this was really cool. This ended up giving him like CD, no, not CD. We should maybe make that equal to EF minus, and then when he had to do the antiderivative again, it actually ended up cycling back and giving him AB. And so he ended up getting into an infinite loop where he always had to take like an extra derivative here. But the cool part about this is that this AB and this AB were here like on both sides. So we ended up actually adding the antiderivative of AB back to the side over here, giving us 2 antiderivatives of AB, which then equaled AB minus EF. And then we divided by 2, and it kind of got us out of this cycle. So hopefully that kind of makes sense here. When you end up doing this antiderivative, ideally this thing right here, when you have to antiderive these pieces right here, hopefully it's done. But it's possible that in order to solve it, you need to break it up into 2 antiderivatives. And this one right here, you might have to break it up into like a GH and an antiderivative of IK. And then this one might have to get broken up into 2 pieces. And eventually you get to a spot where finally you actually don't have any more antiderivatives and you can kind of finally stop. Or this one right here, it actually ended up looping back where this made this made these 2, and then this one was the first one. So, all right, anyways, if that made sense to you, that's awesome. If not, don't really worry about it. But those are kind of the main concepts of integration by parts. So, quick summary then. Let me go back to the first page here. These are a couple of tricks that you can use. You can do substitution or parts, and these are very powerful ways of integrating, especially when you're trying to deal with things that are not quite so straightforward, because a lot of integration, if I ask you to antiderive x squared, you just make it x to the 3 over 3. If I ask you to antiderive e to the 2x, it ends up being e to the 2x over 2. Right? You end up doing a lot of dividing. But if I ask you to do x times cosine x, well, there's really 2 pieces to it. So one option, let things be equal to like the letter u, and then you're going to do a substitution. Or you could break it up into u and dv and try by parts. And sometimes both methods work, sometimes only one method works, sometimes neither method works, and you got to search outside the box for something else. So anyways, get a lot of practice in on this section. I would really recommend don't just do the questions that I assign you, but try finding a textbook and get some practice in, because this is going to be another large part of what you'll do in calculus in university. So, okay, my video is about half an hour. I'll leave her there, and we just have one more left after this. So we'll talk to you guys later.